So today let's discuss about introduction to wind forces and offshore structures. Okay, let's start by considering how wind forces influence offshore platforms, particularly those that extend above the water. Because above the water only we need to calculate the wind loads. Wind can act on various parts of the platform. If you say including the structure itself, some equipment, deck, houses, and any derricks present. Any derricks means like a cranes. So first we need to understand like why do we focus on wind forces specifically in the context of offshore platforms, and then we will discuss about how does the height and the design of the platform impact the way wind forces are distributed across its structure. So we can see that the height of the platform, it really impacts the way wind forces are distributed. If the wind forces varies throughout the height of the platform, how does it impact that, we can see it. And then wind speed classifications, there are two kind of classification. One is gust, other one is sustained winds. So we want to understand what's the difference between like gust and the sustained winds. So wind speeds can be categorized into two primary types. One is gust, another one is sustained winds. Gust means these are the short bursts of wind that usually last less than 1 minute on average. But if you go with the sustained winds that last longer than 1 minute on average and generally more constant. So you can understand the difference between these two. Usually the sustained wind means like these are generally more constant and it lasts longer than 1 minute. But gust means it's lasting less than 1 minute on average. So why is it important to distinguish between these two types of wind speeds when designing or evaluating offshore structures? That we can see this point also. And how might the impact of gust differ from the sustained winds in terms of structural loading? So if you want to see like what's the difference between the gust winds load and the sustained wind load, that we can study in this chapter. Okay, let me explain all these things in the coming slides. So what challenges might engineers face when accounting for these differing wind characteristics in their design calculations? These are the things we are going to understand and study about it, wind forces. Okay, let me explain those things. Okay, let's see like adjusting wind data to standard elevation and averaging periods. There are two things you need to understand, like one is the standard elevation, another one is averaging period. Two parameters are there, we can say. Wind data is typically adjusted to a standard elevation of 10 meters above the mean water level. So whatever the wind speed we are giving it, usually it's getting adjusted to standard elevation of 10 meters above the mean water level. And then for a specified averaging period, such as usually 1 hour like that, we are getting averaging it. So why do we adjust the wind data to a sustained elevation, standard elevation? And then how does this help in comparing wind speeds across different locations and platforms? This point also we will see it. And how does using an average period like 1 hour affect the interpretation of wind data? What could be the consequence of using different averaging periods for wind speed? Like sometimes we use different average wind speed, like 1 hour average wind speed or 1 minute average wind speed, 3 second gust wind. Those things that are there. So we can see what are the consequences of using different averaging periods and where to use and which type of averaging period we have to use. Those things also you will see it. Okay. Adjust the wind data for specific conditions. Wind data can also be adjusted for any specified averaging time or elevation using standard profiles and gust factor that we can see in this APA RP2A section 5.3.2. Okay, how do profiles and gust factors come into play when making these adjustments? So we have to see how do the profile and gust factors come into play when making these adjustments. Why is this standardization important? And what might happen if these adjustments are not made correctly or if they are not applied consistently? What would be the consequences, or what might happen if these adjustments are not made correctly? That also we can discuss about it. So we can see practical implications for offshore design. Finally, let's discuss about the practical implications of wind data adjustments on offshore platform design. How does the understanding of wind force influence the overall design strategy for stability and safety durability of the platform? What are some of the challenges engineers face when designing for extreme wind conditions, such as during hurricanes and typhoons? That also you can see. And we can see further questions. Are there any other environmental factors aside from wind that might be considered for assessing the forces of offshore platforms? how can advancements in technology or data collection improve our ability to predict and respond to varying wind load conditions. Also, we can see it in the discussion. So let's see the use of standard profiles and gust factors. Wind data can be adjusted for different elevations or averaging periods using standard profiles and gust factors. Okay, what are the wind profiles that we can understand? Like, wind profiles describe how wind speed changes with height above the surface. Wind profile means how the wind speed changes with respect to height above the surface, water surface, and these profiles will depend on the surface roughness and atmospheric stability and other local factors also. Standard profiles are mathematical representations that predict wind speed at various height. So different height, different wind speed is there that we can represent using some mathematical representation. That's called a standard profile. So that will allow us engineers to estimate the wind forces at different elevations. So if we have the different elevations, we can estimate the wind speeds using these standard profiles. So next question is, what are the gust factors? We can see the gust factors are used to convert averaged wind speeds, for example, typically sustained over 1 minute or more, into gust wind speed. Anything more than 1 minute, that's average wind speed, we can convert into gust wind speed. For that only gust factors are used. These factors usually compensate for any difference in the peak gust or average wind speeds. So these adjustments are crucial for ensuring that our platforms are designed to withstand maximum wind loads that they might experience during the extreme gust events, right? Without accounting for this gust, we might underestimate the dynamic loading on the platform. That could lead to failure, right, under intense wind conditions. Next question, we can see what would happen if a different averaging period were used. For example, shorter averaging periods, example 1 minute, would capture more of the gust effect, potentially leading to overestimation of wind loads for structures that need to withstand long-term wind exposure. Conversely, longer periods might underestimate peak gust, which are critical for dynamic loading analysis. So, if we are not taking the correct averaging period, then there are consequences. Like, what would happen means, what would happen if a different averaging period were used means. So these are the, either it may be overestimation of wind loads or underestimation of peak gust. So longer period, if we take it, that might underestimate the peak gust. Peak gusts are critical for dynamic loading analysis. In case of shorter averaging period, that would capture more gust effect. That would lead to overestimation of wind load. So we need to see the correct averaging period we have to use it. So if someone is asking you like what would happen if a different averaging period were used, means you can say that shorter averaging periods, that's example 1 minute, that would capture more of the gust effects, that potentially leading to overestimation of wind loads of structures that need to withstand the long-term wind exposure, right? And conversely, if the longer periods might underestimate the peak gust, which are critical for dynamic loading analysis. If you see, wind profiles are commonly logarithmic in nature, right? In this equation, you see wind profiles are commonly logarithmic. So the difference in wind speed between the surface and 10 meters can be significant, especially in areas with high turbulence, especially near the ocean surface. Since because these are commonly logarithmic in nature, difference in wind speeds between the surface and 10 meters, that can be significant. Areas of high turbulence means that's near to the ocean surface. See here, I told you that the wind speed classification, there are two types of classifications, each influencing the design in different ways. Gusts are the short bursts of wind that last less than 1 minute on average. Gusts are highly variable and that represent the rapid fluctuations in wind speed. Gust means like a rapid fluctuation in the wind speed is there. That's what it represents. What's the impact on design means? Gust create dynamic loads that can result in sudden pressure surges on the structure. Actually, that we need to be factored into the dynamic response analysis, example vibration or oscillations. Then consideration for design means our offshore platforms must be designed to withstand the peak gust forces, as well as we need to mitigate some resonant effects or structural damage. that can occur from wind-induced vibrations that we have seen in like vortex-induced vibration we have seen right previously. Next one is sustained winds. These are wind speeds that persist for 1 minute or longer. This is the major difference. You can see anything less than 1 minute on average, that's a gust. That represent usually rapid fluctuation in the wind speed. But if anything that persists for 1 minute or longer, that creating more consistent and continuous forces on the structure, that you could say that is wind is getting sustained. That's a sustained winds. And the impact on design, if you see for the sustained winds, that represent steady aerodynamic kind of loading on the platform, that influencing the overall stability over time, overall structural stability. Consideration for design, if you see the sometimes what happens because of the wind, the fatigue life of the platform needs to be considered under sustained wind conditions, as prolonged forces can lead to material wear and potential failure over time. So in case of sustained wind conditions, we need to consider the effects like the fatigue life of the platforms also we need to consider it. Okay, we will see some example. So here we can see the wind force analysis formulas and wind speed calculation. Mean wind speed at a reference elevation. Here you see u of z, that's the wind speed at a height z, that we can calculate using u0 into 1 plus c. C is the coefficient related to wind profile, and the logarithmic z by z naught. Here z is the height at which wind speed is calculated, and z naught is the roughness length. U naught here, U naught is the 1 hour mean wind speed at reference elevation. U naught is nothing but 1 hour mean wind speed at reference elevation. Uz is wind speed at height z, Uz. U naught means at the reference elevation. And wind speed for a given gust period. The mean wind speed we can calculate at the reference elevation. So whatever the height it comes, it is based on the logarithmic variation z by z naught. And wind speed for a given gust period also we can see. U of U, Z of D. Here Z is elevation, T is the time period. U Z, that's the wind speed at height Z. That with factor like 1 minus 0.41 into IUZ into logarithmic T by T naught is there. IUZ is the turbulence intensity at height Z. So we need to see this turbulence intensity also. What does that mean? T naught is the reference time period and T is the required gust period. T is the required gust period and T naught is the reference time period. And IU is the turbulence intensity at height Z. We can calculate the turbulence intensity calculation. Turbulence intensity IUZ, that 0.006 1 plus 0.131 3.28 U naught. All these factors are okay, minus 0.22 and all it is there, right? So turbulence intensity we are calculating. U naught we know that is a 1 hour mean wind speed at reference elevation. Z is the height at which turbulence intensity is calculated. Z, that's the height at which turbulence intensity is calculated. Z is the roughness length. Wind pressure we can calculate using the P is here. P is the wind pressure, that rho A by 2. Rho A is the air density. U of Z, that's the wind speed at height and time t. So we need to see two factors. One is at time t and height. So wind speed at height and time t, that's a U Z square. You can see this is the it varies with the square term. This is how wind pressure is calculated. Here you can see wind force calculation. Wind force on the given area is Cs into P into A. F is the force. Cs is nothing but the shape coefficient. This we will discuss. And P is the wind pressure. A is the area affected by the wind. Here we will see the examples. One example. Here reference mean wind speed U naught you consider 10 meter per second, and height of interest you see 15 meter, roughness length 0.1, shape coefficient 1.5, area affected by wind 20 meter squared, air density 1.225 kg per meter cube, reference time period 3600 seconds, that is 1 hour. 1 hour mean wind speed, and gust period 60 seconds. So you have all the values T, T naught, Z, Z naught, and C a shape coefficient, everything is there. So we will use this as the example to calculate the wind pressure and wind speed basically. So first step is calculate the wind speed at height Z. So we know u of Z that we have to use it, u naught into 1 plus c into logarithmic value of Z by Z naught. So assume c equal to 0.1 for the typical value for the wind profile. So u of Z, u naught is 10 meter per second and 1 plus c is 0.1, logarithmic 15 by 0.1. 15 is nothing but that height of interest and 0.1 is the roughness length. So with this we can come to know uz value is 15.01 meter per second. So you see the wind speed at reference elevation is 10 meter per second, and 15 meter height the wind speed is increasing from 10 meter per second to 15.01 meter per second. So second step is to calculate the turbulence intensity. Using the turbulence intensity, we have this formula for calculating the turbulence intensity. So if you plug in all these input values, now for the height dependence, Z by Z naught 0.74. Now combining both parts, IUZ becomes 0.062. This is the turbulence intensity is coming. 0.062 is coming, right? We will see how does it impact. Here you could see calculate the wind speed for the given gust period. Using the gust wind profile formula, this is the gust wind profile formula, u z of t. There are two functions, t and z. U z we have already calculated, and logarithmic I u z also we have calculated turbulence intensity, and logarithmic t by t naught also we can calculate. T by t naught, if you see 60 is the second what 1 minute and it is 1 hour. So this value becomes minus 0.4095. So u of z we can calculate 15.01 is that height, and t factor, gust factor is this one, and calculating adjustment we are getting 15.01 into this value, then it becomes 15.17. So 10 meter per second it goes to 15 meter per second, then 15 to 15.17. 15.17 because of the gust effect. Now we can see the wind pressure. We can calculate step 4 using wind profile pressure formula. Wind pressure formula, rho a into by to u of z by square. So we knew those value 15.17 just we calculate. So it becomes 140.62 Newton per meter square. Calculate the wind force. We know this shape coefficient, p is the pressure, a is the area affected by wind. So we can calculate it's 4.22 km is coming. So we know mean wind speed at 15 meter elevation 15.01. Turbulence intensity, it's a 0.06 means 6.2 percentage. So 6.2 percentage in that sense, like 15.01 into 1.062. If you take it also 15.9, like this is turbulence intensity 6.2 percentage, gust wind speed 15.17, wind pressure 140.62 Newton per meter square, and wind force is 4.22 km. So this is the example. This example illustrates how to apply the formulas to calculate the wind forces acting on a structure based on these various parameters, right? If you need further details or different scenario, let me know. Okay, here we can see turbulence intensity equation that we know turbulence intensity IU z, that at height z is given by above sea level is given by the equation IU z equal to 0.06 1 plus 0.043 u naught z by 10 power minus 0.22. Okay, IU z here is the turbulence intensity at height z, represents the relative fluctuation in wind speed at a height, at that height. So turbulence intensity means like that represents how the fluctuation in wind speed happens at that height. U naught is the 1 hour mean wind speed at 10 meters above sea level. So u naught is nothing but 1 hour mean wind speed at 10 meters above height. Z is the height at which turbulence intensity is being calculated. Explanation of the terms. Turbulence intensity means like turbulence intensity is the measures the fluctuation of wind speed at a given height related to the average wind speed at that height. So we know the average wind speed and actual wind speed, how much fluctuation is happening at that height with respect to the average wind speed. So higher turbulence intensity means the variation is high, which are critical means greater fluctuations and which are critical for determining dynamic wind loads on offshore structures, especially in the regions of strong winds and high variability. The term here you see 0.06 into 1 plus 0.03 into u naught. This term adjusts the turbulence intensity based on the mean wind speed. Here u naught is nothing but mean wind speed. So this term adjusts the turbulence intensity based on the mean wind speed above sea level. As the wind speed increases, if the wind speed increases, the turbulence intensity also increases slightly. Here you see wind speed increases, this is 0.043. So wind speed increases means 0.043 plus 1, right? So IUZ also increases. So wind speed increases means slightly 1.043. Turbulence intensity also increases. The factor 1 plus 0.43 U naught reflects the relationship with U naught in meters per second. 0.06 is a factor that scales the overall turbulence intensity. That's okay. There is something called height adjustment, that is z by 10 minus 0.22, right? So the height term z by 10 minus 0.22 is represent how turbulence intensity changes with the height above sea level. So how the turbulence intensity varies above the height sea level. This negative minus 0.02 exponent indicates that turbulence intensity decreases with height. So if you go above the surface, then turbulence intensity is decreases, meaning that wind becomes less turbulent. As you move higher into the atmosphere, especially above the boundary layer, it becomes less turbulent. General interpretation, if you see, as you go higher up in the atmosphere, the wind becomes more uniform, turbulence intensity reduces. This equation models the behavior, showing that turbulence intensity is higher closer to the surface, that is near 10 meters, and decreases with height due to less interaction with the surface and more laminar flow at higher altitudes. If you go higher and higher, it's like a more laminar flow at higher altitudes. That's why the turbulence intensity reduces. That's why this height adjustment factor z by 10 power minus 0.22, that's there. Why use this model? Understanding turbulence intensity is crucial for designing offshore structures to withstand fluctuating wind loads. The turbulent winds create dynamic forces that are typically more difficult to account for compared to constant sustained wind speeds. By adjusting the turbulence intensity based on the wind speed at 10 meters, the height at which structure is located, engineers can predict how the wind gusts will affect the structure at various elevations. So this is how it's useful. This equation is used for wind load calculations for offshore platforms, where high wind speeds, dynamic load from gust turbulence are significant design consideration. Here one more point also I want to explain to you. Here you can see natural logarithmic relationship. This ln t by t naught is the right. This is the natural logarithmic relationship. This represents the logarithmic scaling of wind speed with respect to average time. This reflects how the wind speed at a different averaging period deviates from the mean wind speed at 1 hour. So how much it's getting deviated from the mean wind speed at 1 hour, taking into account the turbulence intensity IU value. That's the factor, this natural logarithmic relationship ln by t naught. With this factor in the formula, we can capture this value. I want to explain something related to design wind speed equation that we have seen in APRP2A, right? So design wind speed U of Z at height Z in meters above the sea level for a specific average time. This T is the averaging time, is given by the following equation. U of Z, that's a design wind speed at height Z in meters above the sea level. This height Z is above the sea level, that you need to understand. And for the specific averaging time T, here you can see the specific averaging time. So it relates the height as well as specific averaging time. Here U of Z 1 minus 0.41 into IU Z into natural logarithmic T by T naught we have seen. U of Z is the design wind speed at height Z for the specified averaging time, and U of this capital U of Z is 1 hour mean wind speed. This capital U Z is 1 hour mean wind speed. That means 60 seconds. Sorry, 3600 seconds. And IU Z is the turbulence intensity at height Z, which quantifies the fluctuation in wind. So what do you mean by turbulence intensity? If someone is asking you what do you understand by turbulence intensity, means then you can say that quantifies the fluctuation in wind speed. Usually the turbulence intensity quantifies how much the wind speed fluctuates over time. A higher turbulence intensity means it implies a greater variation in wind speed. So it varies very quickly, which affects how much wind speed is adjusted for different averaging periods. That's the turbulence intensity. And another one is T is the averaging period, and T naught is the reference averaging time, that is 3600 or 1 hour. That's a 1 hour mean wind speed, as plus T naught is the use that is 1 hour mean wind speed, T naught is the 1 hour averaging time. Here you see wind speed adjustment based on averaging time. This second term 1 minus 0.41, 1 minus 0.41 into I use that, this factor is the right, the second portion of that equation that adjusts that 1 hour mean wind speed to averaging period based on the turbulence intensity and averaging period T. Averaging period T increases, adjustment accounts for decrease in the wind speed variability over time, reducing the effect of short-term fluctuations. So you see that there are two factors, right? So this one factor is the U, that is 1 hour mean wind speed. So if averaging period, if it goes up and up, for example 60 seconds, after that 1 minute, like 1 hour or 10 minutes, like that, if it goes upwards, like if it increases, averaging period increases, means this adjustment accounts for the decrease in wind speed variability. So wind speed variability, it will come down. That means that it reduces the short-term fluctuations. So if the averaging period increases, then you will have the decrease in the wind speed. If the averaging period decreases, you will have increase in the wind speed. Average speed decreases means it's like a short-term fluctuations are more. So that's the reason these two factors are there. You can see there are two important: turbulence intensity and averaging period. Okay.
The relationship, the formula has logarithmic relationship. That's why the formula has logarithmic relationship. The wind doesn't increase linearly with height. The wind doesn't increase linearly with height. It's a log function because the increase slows down as you get higher. The relation, it's a log function. The wind doesn't increase linearly with height. It's a log function because the increase slows down as you get higher. The increase slows down as you get higher. So C here adjusts the rate of that increase based on U naught. The C adjusts here rate of increase based on U naught. Let's dive into an important topic for our offshore platform design. Let's dive into an important topic for our offshore design platform design: the effects of wind on structures. What's that? The effects of wind on structures. Wind forces play a critical role in overall load calculations for any offshore platform. Wind forces play a critical role in the overall load calculations for any offshore platform. So to start, let's explore how wind speed at different heights and turbulence intensity affect the forces acting on a platform. So what are we going to explore? Let's explore how the wind speed at different heights, and turbulence intensity affect the wind forces acting on a platform. So what do you think is the most important thing to consider when analyzing wind loads on an offshore structure? What do you think is the most important thing to consider when analyzing wind loads on an offshore structures? So once again, I'm repeating it. What do you think is the most important thing to consider when analyzing wind loads on an offshore structure? I believe the wind speed at the height of the structure is key. Wind force is proportional to the square of the wind speed. Wind force is proportional to the square of the wind speed. So even small changes in the wind speed can lead to significant variations in the forces acting on a platform. So even small changes in the wind speed can lead to significant variations in the forces acting on platforms. We can use mean wind speed equation to calculate wind speed at different heights. We can use mean wind speed equation to calculate wind speed at different heights. For example, equation for wind speed at height is that, is U of z equal to U naught into 1 plus C into logarithmic ln z by 10. So here U naught is the mean wind speed at 10 meters above sea level. This relationship makes sense. Because wind speed increases with height above sea level, right? This relationship makes sense because the wind speed increases with height above sea level, right? Exactly. But let's not forget the constant C. It's calculated using the equation. This C depends on the mean wind speed at 10 meters. It shows as the wind speed increases, the constant gets larger. Which in turn adjusts how wind speed changes with height. But I'm curious, how does turbulence intensity factor into all these? These relationships make sense because wind speed increases with the height above sea level. But let's not forget the constant C. It is calculated using the equation C equal to 5.73 into 10 power 2 into 1 plus 0.15 into U. This constant C depends on the mean wind speed at 10 meters. It shows that wind speed increases. As the wind speed increases, constant gets larger, which in turn adjusts how the wind speed changes with height. But I'm curious, how does turbulence intensity factor into all of this? Great point. Turbulence intensity is crucial because it reflects how wind fluctuates at a given height. It reflects how wind fluctuates at a given height. It reflects how wind fluctuates at a given height. Wind is not just a steady stream. Wind isn't 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 just a steady stream. It has gust fluctuations. It has gust fluctuations and variability. We can calculate turbulence intensity at height using this equation. We can calculate the turbulence intensity at height using the equation. I u of z equal to 0.06 into 1 plus 0.043 into u naught bracket into z by 10 whole power minus 0.24. So wind isn't just a steady stream. It has gust and fluctuations and variability. It has gust, fluctuations and variability. We can calculate turbulence intensity at height using this equation. So the turbulence intensity depends on the mean wind speed u naught and the height z. So the turbulence intensity depends on the mean wind speed u naught and the height z. The key takeaway here is that turbulence intensity generally decreases with height. Turbulence intensity generally decreases with height. Key takeaway here is that the turbulence intensity generally decreases with height, which makes sense. Generally decreases with height because it makes sense because higher in the atmosphere. It makes sense because higher in the atmosphere, the flow becomes smoother and less turbulent. Because the flow becomes smoother and less turbulent. So we have the mean wind speed. And turbulence intensity. But how do we combine these to get the actual wind speed, which accounts for variations over time? From what I understand, we use this formula: u of z is equal to capital U of z int 1 minus 0.41 into u of z into logarithmic t by t naught. Here t is the averaging period, t naught is the reference time, typically 3,600 seconds or 1 hour. This equation adjusts the mean speed u of z based on the turbulence intensity and time period, right? So we need to adjust the mean wind speed based on turbulence intensity and time period to get design wind speed. So we have the mean wind speed and turbulence intensity, but how do we combine these to get actual design wind speed, which accounts for variations in over time? Yes, exactly. So the design wind speed u of z gives us a more accurate estimate of wind conditions at height z for a given period of time. This is important for understanding how the wind behaves dynamically. So exactly, so the design wind speed gives us more accurate estimate of the wind conditions at height z for a given period of time. This is important for understanding how the wind behaves dynamically. So this is important for understanding how the wind behaves dynamically, whether it is gusting or sustained over an hour. For example, let's talk about the actual wind force that these varying wind speeds generate on the platform. So now let's talk about the actual wind force that these varying wind speeds generate on the platform. To calculate the force acting on the structure, we use equation F equal to rho by 20 u squared into CSA. F is the wind force, rho is the air density, u is the design wind speed, CS is the shape coefficient, A is the projected area exposed to the wind. The wind force is calculated based on the design wind speed we just talked about, as well as the aerodynamic errors of structure. Wind force depends on is calculated based on the design wind speed, as we just talked about, as well as the aerodynamic errors of the structure. The shape coefficient CS depends on the structure's geometry. The shape coefficient CS depends on the structure geometry, such as whether it's a flat surface or a cylinder or something else. And the area A is simply projected area that faces the wind. This is crucial because larger exposed areas will experience larger forces. This makes sense. It's really important to account for variation in wind speed with height and time. Especially in outside environments where wind conditions can be highly dynamic. This makes sense. It's really important to account for the variation in wind speed with height and time, especially in outside environment where wind conditions can be highly dynamic. Do we know if there are any specific gust factors we should apply when calculating gust versus wind sustained winds? Do we know if there are any specific gust factors? We need to apply when calculating the gust and versus sustained winds? That's a great question. Yes, in practical applications, gust factors are often used to adjust the wind speed for a shorter duration gusts, typically lasting less than a minute. This is where the difference between gust and sustained winds becomes important. Sustained winds are those that last longer than 1 minute, while gusts are rapid fluctuations. Sustained winds are those that last longer than 1 minute. While gusts are rapid fluctuations. When calculating the wind loads for gust, the wind speed is typically adjusted by the gust factor to account for these short, high-intensity fluctuations. When calculating wind loads for gust, the wind speed is typically adjusted for this gust factor to account for these short, high-intensity fluctuations. For example, gust would require us to use the higher values of u of z than sustained winds, as gusts exert much higher forces over short periods. Gusts exert much higher forces over short periods. Does anyone have insights on how gust factors are integrated into wind load calculations? Does anyone have idea? Does anyone have insights on how gust factors are integrated into wind load calculations? Yes, the gust factor is usually introduced when we expect high variability in wind speeds, like during stormy conditions. It adjusts the effective wind speed to account for the higher peak wind speeds during gust. It adjusts the effective wind speed to account for the higher peak wind speeds during storm or during gust. This helps in ensuring the structure can handle those extreme but short duration loads. This helps in ensuring that the structure can handle those extreme but short duration loads. This helps in ensuring that the structure can handle those extreme but short duration loads. Exactly, to summarize, we have covered how the mean wind speed varies with height and time, how turbulence intensity impact wind loads, and how to calculate design wind speed. We also discussed how these factors ultimately influence the wind force acting on a structure. We also discussed how these four factors ultimately influence wind force acting on a structure. It is essential that we account for gust, sustained wind, and turbulent nature of wind to ensure that our platforms are designed to withstand the dynamic and often unpredictable forces they will face. Now, as engineers, how do you ensure that we apply these equations correctly to ensure safety in real-world applications? So now, as engineers, how do you ensure that we apply all these equations correctly to ensure the safety in real-world applications? Apply correctly to ensure safety in real-world applications. Do we consider other factors like local terrain and environmental conditions that might impact the wind speed and turbulence? Do we consider other factors like local terrain and environmental conditions that might impact the wind speed and turbulence? Great point. While these equations provide a solid